In section 1.5, we're going to look at the complex numbers. This is a number system that includes the real numbers as a subset. Where the complex numbers were born out of was in trying to come up with solutions to equations of the following type. Let's look at x squared equals to negative 4. It's very easy to see that no real solution, there can be no value of x that's a real number that satisfies the equation x squared equals to negative 4. And to see why, just think about the possibilities for the type of number. First of all, x cannot be a positive number because we know that a positive number squared, a positive times a positive, would not end up giving us a negative answer. So that wouldn't work. Well, maybe x could be negative, but for the same reason, if you take a negative number and you square it, a negative times a negative would also result in a positive, so that couldn't give us the number negative 4 either. If it's not positive, it's not negative, the only possibility would be 0, but 0 squared is equal to 0, and that will not give us negative 4. So there's no real solution to the equation x squared equals to negative 4, but this equation will have a solution in a larger set of numbers, which is called the complex numbers. Okay. So let's define the imaginary unit I. It's going to be defined as the square root of negative 1. And it's going to be such that it has the property that if you square it, I squared, the imaginary unit, will be equal to negative 1. Okay? With that in mind, we can show that the complex number x equals to 2i would actually be a solution to this equation. Why? Well, let's plug it in. If I take 2i and I square it, 2i squared would be 2 squared I squared. 2 squared we know is 4. And by definition of I squared is equal to negative 1. And so that would actually work out. So this equation does have a solution. In the set of complex numbers, it would be x equals to 2i. And it also turns out that x equals to negative 2i would have been a second solution as well. Okay. So also it's the case, so let's suppose if you have a value, let's suppose that a is greater than 0. Then the way that you can handle and break down a negative under a radical like this is to split it apart. You can take out the negative square root part of negative 1 times the square root of a, where now this is a real number because a is greater than 0. The square root of negative 1 is by definition, that's I. And we can write this as I square root of a. Typically, if a was like a nice perfect square, like we're going to see in this next example, the square root of negative 25, we can break that apart as negative 1 times the square root of 25. So when you see the negative under the radical, immediately factor out or take out that square root of negative 1. That's going to become our I term, and then leave the rest of the numbers alone. The square root of negative 1 is going to be I. We also can compute the square root of 25. The square root of 25 is just 5. And so we get the answer I times 5, which is more commonly written as 5i. Similarly, the square root of negative 81, we have a negative under a radical. So let's break that out. We're going to write it as the square root of negative 1 times the square root of 81. The square root of negative 1 is I. The square root of 81 is 9. And so that would be 9i. The square root of negative 17 we have as the square root of negative 1 times the square root of 17. The square root of negative 1 is I. And now square root of 17, that won't break down any. It's not a perfect square, and it's not divisible by a perfect square. So we're going to leave that as the square root of 17. And it's common practice in this case, if you have a radical that won't break down, to actually put the I in front of it. And the reason for that is we don't want to write something like this, where maybe it could be a little bit confusing to some as to whether or not the I is outside or perhaps even inside of a square root symbol. So to avoid that kind of confusion, if you have a radical term with it, just put the I out in front. If it's a nice whole number term, then we'll write I on the right-hand side of that multiplication. So the set of imaginary numbers is the set of all numbers of the form a times I, where a is a real number and I is the imaginary unit. So things like, 4/5 I, -7I, even the coefficient pi times I, etc., or even something like, I times the square root of 3. These would all be examples of imaginary numbers. The set of complex numbers is the set of all numbers of the form a plus bi, where a and b are real numbers. And a would be referred to as the real part, and b would be the imaginary part. So for instance, if we had 3 plus 4i, this would be a complex number. Its real part would be 3, and its imaginary part would be the number 4. So notice that when we say the imaginary part, it's really the coefficient of the I. It does not include the I term itself. Okay. Let's take a look at another one. If we had, let's say, the purely complex number, the purely imaginary number 2i, we can actually think of this as having a real part of 0 plus 2i. So it has a real part of 0 and has an imaginary part equal to 2. So the complex numbers contain as a subset all of the purely imaginary numbers. And if we look at the number 7, let's say -7. -7 can also be viewed as a complex number. It's the complex number that has no imaginary part with it. So you can think of it as the complex number -7 plus 0i. Here the real part is -7, and the imaginary part would be 0. So in this way, you can see that any real number is the complex number of the form a plus 0i. But the complex numbers do include the real numbers as a subset. Now that we kind of have a feel for what these types of complex numbers are, the next thing that we want to be able to do is to do some operations with them. Okay. The first operations we're going to look at is addition and subtraction of complex numbers. So if you wanted to take two complex numbers, let's suppose we had 3 plus 5i, and to it we're going to add -2 plus 4i. In order to add or subtract complex numbers for that matter, all we simply do is add or subtract the real corresponding real parts and the corresponding complex parts. So it's almost kind of like combining like terms. For example, if we look at 3 plus -2, well, 3 plus -2, we know what that's going to give us. That's going to be +1. And if we combine the imaginary parts, we have 5i plus 4i. That will give us 9i. So addition of complex numbers, again, you're just kind of combining like terms. You combine the real parts of the complex numbers, you combine the imaginary parts of the complex numbers, and that combination will be your addition. And not through it. Yeah, that's right. So notice, too, one of the comments I want to make, and this is very important. Whenever you're adding, subtracting, multiplying, or dividing a complex number, we always want to make sure that we write our final answer as a complex number. So make sure it's always written in the form a plus bi. This would be especially important whenever you try to answer your homework questions on WebAssign. Let's do a subtraction one. Let's suppose I wanted to take the complex number 5 minus 11i, and we are going to subtract -6 minus I. In order to subtract these complex numbers, let's first begin by distributing the subtraction in. We have 5 minus 11i, minus a -6 will become +6, minus a -I will become +I. Now we can combine the real parts. 5 plus 6 is 11, and -11i plus a +I will give us -10i. And that would be our final answer. Again, instead of the form a plus bi, where if somebody wants to know This is a complex number whose real part is 11, and whose imaginary part would be the coefficient negative 10. So addition subtraction is pretty straightforward. Let's take a look at multiplication of complex numbers. Essentially, if you think of what it would look like if you had two complex numbers, 2 minus 3i times 7 plus 5i. Each complex number has two parts to it. It has a real part and an imaginary part, which means it's kind of like a binomial. And so really, when you multiply this out, it's essentially the same thing as almost like foiling. To multiply this out, we're going to distribute the real part through first. We're going to do 2 times 7, which is 14. Positive 2 times a positive 5i will give us 10i. We're now going to go ahead and distribute the negative term through. Negative 3i times 7 would give us negative 21i. Negative 3i times a positive 5i. Be careful here. Negative 3 times 5 is negative 15. And I times I will give us I squared. So to multiply complex numbers we distribute, we now combine like terms. 10i minus 21i is going to give us a negative 11i minus 15i squared. We're almost there. We cannot leave our answer like this, because remember, at the end of the day, our answer should look like a complex number. It should be in the form a plus bi. And what we need to recall is that property of the imaginary unit, that I squared is equal to negative 1. So you don't want to leave any answer with an I squared. Everywhere we see I squared, we can replace it with negative 1. So this is going to be 14 minus 11i. We have minus 15 times I squared. Well, I squared is negative 1. This is 14 minus 11i. Negative 15 times negative 1 is now going to be a positive 15. And then combining the real parts, 15 plus 14, that will give us 19 minus 11i. And that's our final answer. So when we multiply the two complex numbers, 2 minus 3i times 7 plus 5i, that product results in the complex number 19 minus 11i. So all in all, the operations with complex numbers are not too bad. Addition and subtraction, again, almost boil down to like combining like terms. Multiplication of complex numbers involves distributing, combining like terms, and especially utilizing the fact that I squared equals to negative 1. The last operation, and this one is not necessarily that intuitive, is division of complex numbers. Okay? To divide complex numbers, it's going to be a procedure. What we need to do is multiply the numerator and the denominator by the conjugate of the denominator. Okay. So what would the conjugate look like? If you have the complex number, let's say 3 plus 6i, its conjugate is simply a matter of changing the sign in between the real and the complex part. So its conjugate would be 3 minus 6i. Similarly, if we had the conjugate negative 2 minus 7i, its conjugate is going to be negative 2 plus 7i. All you're doing is changing the sign in between the real part and the complex part to its opposite. So let's do one of these. Let's suppose that we have 2i divided by 3 minus 4i. So this is division of complex numbers. We're trying to divide the complex number 2i by the complex number 3 minus 4i. In order to do that, we need to multiply the fraction, top and bottom, by the conjugate of the denominator. The conjugate of 3 minus 4i, we said it a minute ago, that's going to be 3 plus 4i. Just change the sign in between. So we're going to multiply both top and bottom by 3 plus 4i. The rationale and the reason for doing this, some of you might recall this. This is essentially kind of analogous to rationalizing a denominator. In a previous class, you would see that if you have an expression that has a square root in the denominator, then we would want to get rid of that square root. Well, the 2i, remember, what is I? I is really like the square root of -1. So even though we're not writing it, it's essentially like having a square root in the denominator, and that's why we're using the conjugate to rationalize the denominator here. So let's go ahead and multiply this out. In the numerator, we're going to have 2i times 3 plus 4i all over 3 minus 4i times 3 plus 4i. If we distribute in the numerator, 2i times 3 is going to give us a 6i. 2i times 4i is going to give us an 8i squared. Divided by, in the denominator, we have to distribute it out. 3 times 3 is 9. 3 times 4i is a positive 12i. Negative 4i times 3 is a negative 12i. And a negative 4i times a positive 4i is a negative 16i squared. In the numerator, we can already replace that I squared with -1. So it's going to be a -1 here. In the denominator, the positive 12i and the negative 12i cancel. So we get 9 minus 16i squared. The numerator is 6i. Positive 8 times -1 is going to be a -8. All divided by, in the denominator, again, I squared is -1. So everywhere we see that I squared, we're replacing it with -1. That's going to give us 6i minus 8, all divided by negative 16 times -1 is a positive 16. We get 6i minus 8 over 25. And while this is correct, we're not done yet because we haven't written it in the standard form yet. Again, when you divide or do any operations with complex numbers, your answer, your final answer should look like a complex number a plus bi. To do this, let me rewrite the numerator. Let's put the real term first, the complex term second, all over 25. And now what we're going to do is we're going to split apart the numerator. We can write this as -8 over 25 plus 6i over 25, or 6/25 I, and then that would be our final answer. So now it looks like a complex number. It's the complex number whose real part is -8/25, and whose imaginary part would be 6/25. So division of complex numbers, it's kind of a technique that you have to remember. It's not inherently obvious when you look at it what you need to do. The technique, the way we divide complex numbers, is we multiply the numerator and the denominator of that division by the conjugate of the denominator. That will essentially rationalize the denominator. It turns the denominator into a real number. In this case, it was 25. And then you can split apart the resulting numerator to write your answer as a plus bi.